Now we will talk about the kinetic theory of gases. We will not discuss this theory in great details, as this would require a few lectures, but we will focus on the intrinsic assumptions and on the important conclusions that can be drawn from this theory. The kinetic theory is a physical model of the gas state, where the gas particles, atoms or molecules, are assumed to have specific properties. First, it is assumed that the particles do not interact with each other. They exhibit neither attractions nor repulsions with each other. This implies that the energy of each particle is only kinetic in nature. Second, gas particles have no volume. Hence, they can travel within the whole volume of the container and are not restricted in their motion by the presence of other molecules. So, if two particles came in contact, they would just fly through one another. This second assumption is consistent with the first one, which considered that gas particles do not interact. The third assumption is that gas particles travel in straight lines between collisions with the walls of the container. Furthermore, the collisions of particles with the walls are assumed to be elastic, implying that particles do not lose energy as they bounce off the walls. Finally, the model assumes that the kinetic energy of the gas particle is equal to the thermal energy, which we said earlier is proportional to R times T. The first two assumptions are by far the most important to remember, and that is why they were written in bold. They are especially important because they are the least reasonable. We know that real molecules do interact with one another and do occupy space. However, without these two assumptions, none of the important conclusions from the kinetic theory of gases would be obtained. The last two assumptions are very good assumptions that make sense physically. The kinetic theory uses these four assumptions as well as the fundamental laws of mechanics, in other words, the laws of motions proposed by Newton, and then considering the average behavior of particle, it comes up with the amazing prediction that the gas pressure is expressed in terms of volume, temperature, and number of moles, exactly as found by combining Boyle's, Charles, and Avogadro's laws. In other words, the kinetic theory of gases makes the prediction that gases should follow the ideal gas law. Now, the important implication of what I just said is that if you remove any one of the above assumptions, then you cannot reach the conclusion that PV equals nRT. So, we must conclude that for a gas to behave ideally or perfectly, then the interparticle interactions must be negligible. As we discussed earlier in this lecture, this will occur if gas particles remain far from each other most of the time. This also confirms the fact that the energy of an ideal gas is equal to the kinetic energy of its particles, and most importantly, it tells us that the energy of an ideal gas depends only on temperature. Conversely, if we think about solid, liquids, or even gases at high pressure or at low temperature, their particles are much closer to each other on the average. Hence, the interparticle interactions have a much larger magnitude and can no longer be neglected in comparison to the thermal energy. We will see later in this class that for these other states of matter, the energy of the substance varies not only with temperature, but also with the volume. This should make sense to you since you recall that a change in the volume of a substance leads to a change in the average distance between its particles, hence to a change in the potential and the total energy of the substance. So we should not expect the ideal gas law to work for gases at low temperature or high pressure, or for liquids or for solids. For these substances, other equations of state must be used. Such equations of state must account for the strength of the intermolecular interactions and for the volume occupied by the particles. An example of such an equation of state, which you have heard about in general chemistry, is the van der Waals equation of state. This equation of state actually works much better than the ideal gas law for gases at high pressure or at low temperature. We are not going to discuss this further since gases, which we deal with routinely in the life sciences, behave ideally under most circumstances. Another great achievement of the kinetic theory of gases is its ability to predict the frequency of collisions between gas molecules. Why should we think this is a significant achievement? Well, chemists are often interested in the mechanism of chemical reactions. For molecules to react, they have to come in contact with one another. Actually, for reactions to take place in a gas phase, the intermolecular collisions need to be powerful enough to lead to the rearrangement of the electronic structure of the atoms and the formation of new chemical bonds. So, a first step toward a better understanding of the mechanism of chemical reaction always requires us to estimate how often molecules collide and how strong their collisions are. This is what the kinetic theory of gases allows us to learn. Finally, the kinetic theory of gases provides a prediction for the mean speed of molecules as a function of the absolute temperature and the molar mass of gas particles. This specific point will be discussed in more details on the next two slides.